Next topic is arenes. First, how we define arene. These hydrocarbon. So there are two major classes of the hydrocarbon or in organic chemistry. Aliphatic. What is aliphatic? Means it can be straight, it can be branched, or even it can be a cyclic compound. Aromatic. What are aromatic or arenes? Include one or more rings of a 6-carbon atom with a delocalized bond. So aromatic compounds always they should have a, this is a skeletal formula. So they have a ring of 6 carbon with a delocalized electron. What delocalized means? That the double bond can be with 1, 2, 3, 4, 5, 6. So double bond can be between 1, 2, 3, 4, and 5, 6. And next moment, the double bond can be between 2 and 3, 4 and 5, 1 and 6. So it's a delocalized means the double bond is continuously changing its position, but it is alternative double bond means one molecule means one part of a molecule have double bond, then there's single, then double, then single. So aliphatic compounds are straight or a branch hydrocarbon are called aliphatic. All the chemistry what you studied till now, all the elements you studied were aliphatic. But now aromatic compounds, aromatic means why we use the term it's from aroma means because these compounds have a distinctive smell whenever a compound is having a benzene ring. So first copy this part. The main topic is arenes. Then the first person to explain the idea of a benzene ring was a Kekul's model in 1865. What he suggests that the benzene ring is actually a combination of 6 carbon atoms in a ring So this was a Kekul's model. He suggests the formula of a benzene ring is C6. He did calculations as well, some calculations. But this was initially theory given by Kekul's, and he suggests that 6 carbon atom bonded alternative double bonds are there. And so if there are, if so 6 carbon atom alternative double bond and one bond or single bond with hydrogen, the formula of benzene ring is C6 and H6. But the problem with Kekul's model, what he did not mention that these bonds are, he suggests that these bonds are stationary. So if these bonds are stationary and there are double bond, so one thing from Kekul's structure, benzene should be highly reactive first thing. Because if a compound, alkenes are more reactive than alkane because there's a double bond, so they are more, they have greater tendency for electrophilic reactions. So benzene should be highly reactive, but practically reactions of a benzene are not occurring at room temperature. We have to heat the benzene about 60 degree centigrade to supply to start up the reaction. 50 to 60 or 40 to 60 vary from different compounds attached to a benzene ring. So it should be highly reactive, but benzene is not highly reactive. According to a Kekul's structure, because there's a double bond, so there should be addition reaction. But practically benzene are not having addition reaction, it is having substitution reaction. Then as he suggests, there's the carbon-carbon double bond and carbon-carbon single bond. So if there's a double bond and single bond, so the bond length should be different. Means C double bonded with C length and C single bonded to C, there should be different bond lengths. So, but X-ray diffraction shows when we pass the X-ray, we find that all the bonds in a benzene ring have the same length. All the carbon bonds, even it's a double bond or a single bond, they have the same length. And there's also a thermochemical data for a benzene ring. Because when carbon double bonded with carbon, and if we add hydrogen, one molecule of hydrogen, so when the carbon carbon, it will turn into single bond. But as the double bond changes into single bond, the energy, which is energy change, which is occur, is minus 120 for one bond. So when one molecule of hydrogen added to carbon-carbon double bond, energy is minus 120. So if three molecules of hydrogen are added, what should be the energy? The energy should be minus 360, because each bond, first bond will break and the bond form, the energy change is minus 120. Minus 120, minus 120. So overall energy change should be minus 360. But practically it's not 360, it's minus 208. So practical value and the theoretical value, theoretically, this is a model given by the Kekule, but practically, when if we calculate the energy required for addition and we calculate the energy release or energy release for carbon-carbon double bond when hydrogenation for three water hydrogen molecule, it's minus 3, it should be minus 660, but practical data shows it's minus 208. That is why, so there are a lot of drawbacks in the Kekule structure. That's why his structure was rejected. But the base of the structure based on Kekule model, but according to Kekule, according to his model, the carbon-carbon double bond is a stationary. But in practical, these bonds are not stationary. These are vibratory double bonds. Means what happened when there is a carbon-carbon double bond, next moment the double bond position will change. So this double bond position is continuously changing. So as the double bond position continuously changing, it shows that it is not a normal double bond. It is actually a vibratory double bond. And due to this vibratory double bond, if there is an electrophile is attracted toward this side, electron rich. But next moment, electron rich side will be the other. So electrophile move to other side. Next moment, so it continuously changes. As it continuously changes, electrophile does not find a space to attack at a specific location. That is why the benzene is stable at room temperature. Is it clear? The concept of Kekule model and why his model is rejected.
Yeah.
So this is the same thing like enthalpy change of hydration. Just I discussed enthalpy change when one hydrogen molecule added to cyclohexene. So it is energy is minus 120. If we have a benzene ring, according to Kekule model, if we have a benzene ring, because according to Kekule, the double bonds are stationary. But in reality, the double bonds in a benzene ring are not stationary. They are delocalized double bond. They continuously changes the position. So this hydrogen, when added according to Kekule model, it is minus 360. But in reality, it's only minus 208. So when we make a sketch a graph, so example, if we have a according to Kekule model, if we have a benzene ring and we have the modern explanation of a benzene ring, so how we represent a vibratory double bond? So we make a circle inside that we don't specify a position of a double bond. The double bond can be anywhere. So theoretical data, because the reaction is exothermic reaction, reactant have high energy and the product is having low energy. So if you want to convert Kekule model of benzene to a cyclic alkane, and if you want to convert the modern benzene into cyclic alkane, modern benzene required a small amount of energy, Kekule model required greater amount of energy. So this is the extra energy which required from Kekule model, and this gives an evidence that the benzene ring is more stable according to modern explanation rather than Kekule formula. So minus 152 kilojoule per mole is actually the energy which these delocalized electrons have. Copy this.